Hello everyone, this is Mr. Fish. Today we're going to be talking about tides, and by the time this thing is over, I hope that we understand three ideas much better than we did when we started. First of all, I want us to be able to understand what is a tide in the first place. When we talk about tides, what is it that we are talking about? Second of all, I want us to understand the two different types of tides. And I'm not just talking about high and low tide. There's two specific types of tides that we are going to be learning about. And finally, we need to know how the lunar cycle impacts those tides. This unit has been all about the lunar cycle. Now we're talking about tides. There has to be some kind of connection. So first, let's talk about what a tide is after all. We need to understand that first before we can talk about anything else. When we talk about tides, the dictionary is going to tell you that a tide is the periodic rising and falling of the oceans and ocean inlets. Okay, great. So what does that mean? Well, let's say you're at the beach. Maybe you've noticed that if this is the beach here, let's say this is the beach, and you're at the beach and here's the water. Maybe throughout the day you notice that that water goes higher. When you first got there, the water was all the way down here on the beach. But now, throughout the afternoon, you notice that the water is higher. That sandcastle that you built right here, it's getting washed away. It was fine before. Now it's a problem. Then, later on in the day, that water recedes. Okay? There are names for that. Real basic names, not the names that we're going to be learning later on, but real basic names. When the tide is all the way up here at its highest point, guess what? That is called the high tide. Down here at the lowest point, that is called, no big surprise, low tide. I can do all of the drawings that I want, but the truth of the matter is you're not going to get the idea unless we really see it going on. So this is a time-lapse video of an area in Nova Scotia. You can see it's in Halls Harbor, Nova Scotia. 1.5 minutes. Watch what happens to the tides here. It's absolutely incredible. Remember, this is a time lapse, so it's very sped up. This is going to happen over about a 12-hour period. Now check it out, all that water coming in from the ocean. It's coming in so significantly that it's even lifting up the boats. Watch the boats closest to you. In fact, the entire pier is now moving. That water didn't used to be there. It wasn't there earlier in the day. Now there's so much water, it's actually lifted up the entire pier and all of the docks. And then, so that's the high tide point. The water then starts to recede again. The docks go down, the boats go down. Watch these closest to us. They're going to settle out on the ground. There they are. And the water goes back out. Down to low tide. Absolutely incredible. So now that we know what tides are, it's important to understand that not all tides are the same. Just like everything else we've been talking about this year, these tides occur in cycles. There's two main types of tides that we need to understand and learn about. The first is called the spring tide. Now, it's important that you understand that this is not talking about spring like with flowers and, the season of spring. No, that is not what we're talking about. Instead, I want you to think more like a spring, like something that can bounce really high. Here's why. Spring tide is the highest tides of the cycle. And there are approximately two spring tides a month. 2 per month. 2 spring tides. Not spring the season, spring like bouncing up the highest tides possible that month. So that's the spring tide. The second type of tide that we need to understand is the neap tide. Yes, neap. I said it, neap. Yep, that's right, neap. Don't ask me why they call it neap. I think it has something to do with some old English word. But anyway, it's called the neap tide, all right? And the neap tide is one of the lowest tides of the cycle, okay? So the neap tide is the lowest tide of the cycle. That's a T right there. And it also happens approximately 2 times per month. So now that we know that the spring tides have the highest high tides and the neap tides have the lowest high tides, it's important to try to understand what these tides look like from space, or at least one way to model those tides from space. So let's say that we've got the Earth, okay? We're looking down on the Earth. This here is the North Pole, okay? And this blue oval that I'm pulling up is going to represent the Earth's oceans. Now we're going to call this a tidal bulge. So we are going to label that right here the tidal bulge. Tidal bulge, just like that. And if you remember, of course, the Earth rotates counterclockwise on its axis once every 24 hours. So every point on the Earth is going to pass through one of these tidal bulges twice a day. Let's make it a little easier to see that. We're going to put a dot right here on the coast of California, right there. Now, if you watch, right about now, at this point in the day, that dot in California is at its highest tide, right? As we continue to rotate throughout the day, low tide. Then the tide starts to go up again, high tide, low tide, and then back to about where we started 24 hours later. 2 high tides, 2 low tides. Okay, so now we understand sort of that idea of the tidal bulge. We understand why there's going to be 2 high tides and 2 low tides during every 24-hour period. But what does that have to do with the lunar cycle at all? Well, it's all about gravity and the gravitational attraction between the moon, the sun, and the Earth's ocean. So let's take our tidal bulge diagram again, and we're going to add in this time our lunar cycle. So there's our tidal bulge. Here's our Earth. But now we also need to add in the sun and, of course, the moon. Let's start with a situation where we're at a full moon. Okay? So the Earth is between the moon and the sun. The 50% portion of the moon that is illuminated is facing us here on Earth. We can see the whole thing, so that would be a full moon. Now, of course, this isn't to scale, but work with me here. The sun is pulling on the Earth and everything on the Earth in this direction. The sun's really far away, but it's really, really big, so it's got a lot of gravitational attraction. The moon is a lot smaller, but also a lot closer to the Earth. It's pulling in this direction. And it's not only pulling the the Earth, but it's also pulling the Earth's waters. That's what creates the tidal bulge. And guess what? When we have the sun, the Earth, and the moon all lined up all together, we've got the sun pulling this way, we've got the moon pulling this way. This is going to be one of our spring or extreme tides. Our spring or our extreme tides. Now let's have our moon revolve around the Earth in the counterclockwise direction until it is in this position. Of course, this would be the last quarter or the third quarter. Well, now that tidal bulge doesn't look the same. It's a lot smaller, and it's looking like this, the other direction. Now, of course, the moon, like we said, is pulling on the Earth's oceans. But because the sun, the Earth, and the moon are no longer all in a line, the moon and the sun's gravitational forces are no longer acting together. That makes it less. Now, the major component is the moon. It's a lot closer. But the sun, like I said, is so huge, even though it's really, really far away, that it acts to counteract some of the gravitational pull from the moon. This is what gives us our neap tides. In other words, our lowest high tides of the lunar cycle or the tidal cycle. They're both cycles. And this happens not just at the last quarter, but also if we take our moon and we have it revolve around the Earth to the first quarter, guess what? It's going to happen here as well, because we have the gravitational attraction from the moon acting on the Earth's oceans, pulling in this direction. But that gravitational pull is being counteracted by the gravitational pull from the sun, so it's not going to be as extreme as if they are all lined up together like they were for the full moon. Now, speaking of full moons, let's take a look at the entire lunar cycle. We're starting here at the first quarter, and we've got our neap tide, the lowest of the high tides. If we take our moon and we move it through the lunar cycle in a counterclockwise direction, revolving around the Earth, here we are at the full moon position. Of course, the 50% of the moon that's illuminated is facing the Earth. We can see it. Now, the gravitational pull from the moon and the sun are acting together. They give us our spring tides or our extreme tides. Continue to revolve the moon around the Earth in a counterclockwise direction. Here we are in last quarter, giving us once again our neap tides. And finally, the moon revolves until it is right between the sun and the Earth. The 50% of the moon that's illuminated is totally facing away from us, and we have the new moon phase. Now guess what? This is where we have, once again, our spring tides, our extreme tides. Just like that. Now I understand that this one is a little bit more difficult to comprehend. I mean, over here, when we're in the full moon, you can understand that the water on this side of the planet is being pulled this way by the moon, and the water on this side of the planet is being pulled this way by the sun. But what about this situation? I mean, it's really easy to understand why this tidal bulge is happening, but what about this tidal bulge? Well, it's still all about gravity and what's pulling what. The sun and the moon's gravitational attraction on the Earth and the Earth's waters and the Earth's oceans are all pulling in this direction. And it's pulling the water, it's pulling the Earth, and it's pulling the oceans over here as well, but it's not pulling those oceans quite as much as it's pulling the Earth. So it's going to pull the Earth a little bit more, leaving these oceans out here. Now, I know that's a lot to understand. You might want to think about it in a different way. Let's imagine you've got a cup of water. Okay? And that cup, well, let's put some water in it. That would be helpful. All right, so we've got a cup. It's got some water in it. What's going to happen to that cup if you reached and grabbed it and pulled it in that direction really fast? Think about it for a second. Do the mental modeling in your head. What's going to happen is that line right there in the water, it's going to tilt. It's going to bulge out just a little bit. It's going to tilt because of inertia, right? Takes a little while for the water to speed up, so the water level is going to tilt just a little bit when you jerk it. Think about the moon and the sun pulling on the Earth, and that water is kind of being left behind, just like the water in that glass. Now, I had an idea. I wanted to try to show this to you. I wanted to try to demonstrate it. So I built this, my Tidal demonstrator of science. And what it is, I've got this scooter. On the scooter, I've got a beaker. I've got a rope attached to the scooter. And this little thing here, where it turns out I placed my phone. That's where I videotaped everything from. Now, in this model, the beaker and the water inside the beaker represents the Earth's oceans. Now, the rope right here, that represents the combined gravitational attraction of the sun and the moon. And me, well, I'm over here. I'm over here pulling on the rope. I represent the sun and the moon. Now remember, here's the beaker sitting on the scooter. Camera's down here. And I'm getting ready to tug this scooter. See, it's me. See? Check it out. Right there. The beaker is heading in this direction. I'm pulling in this direction, and yet the water inside the beaker is sloshing in this direction. It's sloshing in the opposite direction. That's the whole point. Remember, we were looking at the tidal bulge over here, and we were wondering if the Earth is here, if we've got the moon and the sun pulling in this direction, it makes sense now why we might have a bulge on the opposite side. Let's go back here. See, I'm pulling in this direction. We've got our bulge. We've got our higher water on the other side. Now, this thing worked great for the first half a second. Then it started bouncing around. You couldn't see it anymore. But it's kind of cool to see the hallway from this perspective, so I'm going to let it run through. So the whole point of that insanity was to demonstrate for you how the combined gravitational attraction of the moon and the sun, even in the new moon phase of the lunar cycle, jerking the Earth and its oceans in this direction can cause a tidal bulge not just on this side of the planet, but also on this side of the planet. Well, we've covered a lot of ground. But at the end of the day, there are really three things I'm hoping you take away. First of all, the tides. When we talk about tides, we're talking about the periodic rising and falling of the oceans. It happens in a cycle. And that cycle includes two extreme tides, or very high tides, and those are the spring tides. And then two high tides that are lower than all of the other high tides of the cycle. Those are the neap tides, the lowest of the high tides. And finally, folks, there really is a relationship between the lunar cycle and the tidal cycle. We have our spring or extreme tides at our new and our full moons, and we have our neap tides at the first and last quarter. Thanks a lot. Hope you enjoyed it.